Hello. A couple days ago I made a short video on how to collimate a Newtonian telescope using a laser collimator. This is an addenda to that video because there's a special case, and that's telescopes that use the Bird-Jones design. I want to explain what that is and how it's different and what it will look like if you use a laser collimator on a Bird-Jones designed Newtonian. To start with, modern telescopes use a parabolic mirror. It looks like this here. Telescopes used to use a spherical mirror. A spherical mirror is like you cut a bowl in half, and it's the bottom half. A parabolic mirror is like you smash the bowl down after you've cut it in half. So it's not the same distance from every piece of the circle. With a parabolic mirror, no matter where the light hits it, all of the light focuses at a single point. With a spherical mirror, it doesn't all focus at the same point. So spherical mirrors suffer from something called spherical aberration, where the views are a little fuzzy. They're not too bad in the center, but the farther you go out from the center, the fuzzier they get. For most folks, when they first start off, probably won't even notice it. And if you're looking at something like a faint nebula, hundreds of thousands of light years away, it's hard to notice it anyway because they're kind of fuzzy to start with. They're big billowing clouds of gas. But if you're looking at the moon or one of the planets, it is definitely noticeable if you have spherical aberration. It used to be that pretty much all telescopes, Newtonian telescopes, use spherical mirrors. Parabolic mirrors were very difficult and expensive to make. Eventually, they come out with a fairly cheap way to make parabolic mirrors. And when that happened, most all Newtonian telescopes with a mirror 6 inches or larger switched over to the parabolic mirrors. Some companies switched over even for smaller apertures. Orion, for instance, made 114 millimeter Newtonian, 130 and 134. They were all parabolic. Most companies, however, have stuck with the spherical mirror for entry level Newtonian telescopes to keep the price down. They're trying to keep the price down low. By the way, Orion didn't keep the price down. They went out of business because they were making too good a telescope for what they were charging, because they were charging the same thing for their telescopes with a parabolic mirror that most other folks were charging for a spherical mirror. There are a couple of telescopes that still use the spherical mirror. This is one of the two. It's called a Schmidt-Cassegrain. The other one, by the way, is called a Maksutov-Cassegrain. I don't have one of those right now. I gave mine away. But a Schmidt-Cassegrain uses a spherical mirror, and it has a piece of glass in the front called a corrector plate, which corrects the spherical aberration. For some reason, they chose not to switch over to the parabolic mirror with Schmidt-Cassegrains, which suits me because that big hunk of glass in the front keeps out dust and mosquitoes, other things. Newtonians don't have that. They have an open front. So all kinds of stuff can get down into the tube, and you have to clean the the mirror in the back on a regular basis. There used to be something called a Schmidt-Newtonian. Yeah, there's a picture of it. Schmidt-Newtonians had a corrector plate in the front, just like the Schmidt-Cassegrain does. But when they switched to the parabolic mirror, they quit making Schmidt-Newtonians because they were going to just put a parabolic mirror in them. There are still some low-end telescopes that use the cheaper spherical mirror. Here's one right here. This is a National Geographic 114 millimeter Newtonian telescope. Regular Newtonian, and it has a spherical mirror. The one behind me, this one right here, also has the exact same length as this, but it doesn't have a 500 millimeter focal length like the National Geographic. It has 1,000 millimeter focal length, and that's because arithmetically, if something is an F10 or better, it corrects the spherical aberration. There are a couple ways to address spherical aberration when using a spherical mirror. One is reduce the aperture. The smaller the aperture, the less spherical aberration you have. Another is increase the focal length. The longer the focal length, the less spherical aberration you have. This little telescope has a 76 millimeter aperture, a little small aperture, 900 millimeter focal length. So it doesn't have much in the way of spherical aberration. Another way is to increase the focal length using a corrector lens inside the telescope. Not up here, but inside. That's called the Bird-Jones design. What they did was they took the corrector plate off the front, reduced it so it was cheaper to make. You have to, when you grind the mirror, you have to grind the corrector plate at the same time because they have to match up. And they would put the corrector plate, the smaller one, in the center of the telescope before the secondary mirror. The idea nobody bought it. They didn't make any of them. They came up with the design, but it never sold. Someone came up with the idea, however, what if we just took and put a little corrector plate in the bottom of the focusing tube, which is basically a Barlow lens, which would double the focal length. That's why this little scope has 500 millimeters of length, but 1,000 millimeters of focal length. It has a Barlow lens in here, in the bottom of the focusing tube. That design actually has a couple advantages. For one thing, the tube is shorter, so it's easier to store. You put it in a suitcase, takes up less room, kind of like a Schmidt-Cassegrain. This has a 1,500 millimeter focal length, and it's only about 300 millimeters long. This, by the way, is called a catadioptric because it has a primary lens and a primary mirror. It's got both. And in a way, this is a catadioptric. It's got a primary mirror and a correction lens here, which you could call a primary mirror or a primary lens. And it's not it's not disadvantageous, except if you're trying to collimate the thing with a laser collimator. With a laser collimator, you turn on your, oh, by the way, if you haven't watched part 1, the first video I did, collimating a Newtonian with a laser collimator, watch that one before you watch this one. Could have told you that before you watch this one, but I didn't think of it. Oh, as long as we're there, please subscribe. I need subscribers, fella. I ain't got none. Alright, I just turned on the laser collimator. You can see the laser hit the primary mirror back there. But it's not a laser beam, it's a laser splotch. It's a laser splotch because the laser is traveling through this corrector lens. And the corrector lens refracts the laser. So it's no longer a laser, it's a flashlight. Plus, on inexpensive scopes where they use the Bird-Jones design, they don't bother putting a center spot in the mirror. So when I collimated this, I had to estimate where the center of the mirror was and then estimate where the center of the splotch was. I did a little video on how to add a center spot to your Newtonian reflector if it doesn't have one. Watch that video, add a center spot, and this will be a lot easier. Took me about 20 minutes to do that. On the other end of the scope, we have the laser that's supposed to go behind. There's supposed to be a laser dot here which goes behind that little dot. It won't fit behind the dot, however. What you have to do is, oh, it's a splotch, a big splotch, because it's been bouncing around a while, and it's the exact same width as the outer circle in the aiming reticle. That's where I got it centered. If I move it at all, any direction, you can see it's no longer centered. You can get a fair collimation doing that with a laser collimator on a Newtonian with a corrector lens in it. However, it's a lot easier if you add a center dot. And don't expect a little laser dot anywhere. Expect a laser splotch. Fairly big in the front and bigger in the back. And that's pretty much all you need to know about how to collimate a Newtonian telescope of the Bird-Jones design. It's just got a little corrector lens in there, which makes your laser dot into a flashlight light, a splotch, and you just center the splotches. Once you've done that, you can do, by the way, with a laser collimator, one of the advantages is you can do it in the dark at night. So you can take the telescope out, collimate it as best you can that way, and then point it at some stars. If stars look like little pinpoints, you've made it. If they have coma, they have tails, you haven't made it. So fiddle with it a little bit more. And of course, once you get it fiddled with successfully, do like I did this one, and lock it down. I did this some months ago, and I haven't had to collimate it since then. It's holding the collimation pretty well. And yeah. So until we meet again, happy trails.